One of the things we need to first understand about energy is that it's an incredibly broad term. It can apply to many different forms, which we'll look at in a second, and it's actually fairly difficult to try and define. So if you look up the technical definition of energy in a textbook or online, you'll typically see the ability to perform work. Now that's weird for two reasons, because in your day-to-day life, work means one thing. In physics, it means something else entirely. The other thing is, as you start to understand more, it becomes a fairly circular definition, because energy is the ability to do work, but work is really like the change in energy. So when you change something's energy, you perform work. So the work is the ability to change the thing that you use to perform work, which is the thing that you just use to change the thing. You wind up going in this very circular pattern. It's a fairly abstract concept, energy and work. I think it becomes more concrete and easier to understand once you jump into the math. So for now, I do want to point out that the technical definition of energy is the ability to perform work. The less technical definition, and what we will work with for now, is the ability to do stuff. Turn on lights, move, heat things up, increase the volume, use your television, use your washing machine, whatever. In order to do things that we normally want to do, you need energy. Okay, so that's what we're going to kind of define it as at the moment. The ability to get stuff done. Again, probably not going to make you feel super confident in energy and its definition, but it'll give us a start for right now. So we are very specifically going to look at a form of energy called mechanical energy. Now we'll discuss more in a second, but mechanical energy is the energy associated with an object's position in space, where it is, or its velocity, how fast it's moving. So those are the two things that we're going to discuss. There are several more. So you've got solar energy, you've probably heard of nuclear energy, thermal energy, which is just heat, electric energy, that's what we use to power all of our devices, hydroelectric, that's like Hoover Dam, if you use moving water to generate electrical energy essentially, geothermal, the heat of the earth, we can use that and convert that into other forms that are more useful, chemical energy, that's what we get from our food, wind, you've seen wind turbines, we can use wind energy, sound is a form of energy, we've got electromagnetic energy, there's several different forms. We are exclusively going to focus on mechanical energy, the energy associated with where an object is in space and how fast it's moving. We'll make general connections to these others and see how everything overall is connected with an energy, but our analysis for this chapter will be specifically on mechanical energy, so just get used to differentiating between energy as a whole and mechanical energy, which is a very specific subset of energy. All right, so if we want to look at mechanical energy in a little bit more detail, we need to realize that there's two categories within mechanical energy itself. So if you think about it kind of like a drop-down menu, we've got energy, which is all the types I showed you. Then underneath that, we've got mechanical energy, which is one of those types. And then beneath that, a further subset is potential energy and kinetic energy. All right, we're going to start with potential energy first, and potential energy is essentially just stored energy. The word potential means to store. You have the potential to do something in the future, you may be able to do it, so you're holding on to that. At some future time, we may use this. And again, there's a further subset under potential energy, and that's going to be gravitational potential energy, which I will refer as capital E sub G, and elastic potential energy, which I will refer to as, it says here EE, but I am going to refer to it as EEP. So moving forward, that is the elastic potential energy. To define those a little bit more clearly, gravitational potential energy is the energy associated with an object's position in a gravitational field. Now that's very technical. It basically means when I hold things higher in a gravitational field, they will have more energy. It's why when you drop things from higher up, they smash into the ground more violently. They have more energy just from being stored so high up in a gravitational field. It's why peering over the ledges of balconies, at least for me, are more terrifying when you're multiple stories up as opposed to maybe when you're on the first floor, the second floor. Because you innately understand that, like, if I fall from here, it's going to be worse for me. And that has to do with this gravitational potential energy that's being stored in your body at those locations. When you're higher up, you'll have more of this energy. The other one is elastic potential energy, and that is the energy associated with anything that has what we call elastic properties. Elastic just meaning it will return to its original shape after you've deformed it. You stretch it, you let go, it returns to its original shape. You compress it, you let go, it returns to its original shape. So that'd be something like a spring, a rubber band, etc. And there's energy stored when you deform those. So it's why you can use like a slingshot. I take a pebble, I put it in the slingshot, I pull it all the way back, I've stored some energy in this elastic band, and when I let go of it, boom, that will shoot that rock and it will be some other form of energy. But I can store energy in things that I can compress that are designed so that they can rebound and go to their original shape. All right, the next one would be kinetic energy, which I will refer to with as E sub k, and that is simply the energy associated with an object's velocity. So the first two, gravitational and elastic potential energy, are really stored energy associated with where you are in space. Are you high up or low in a gravitational field? Have you compressed something like a spring that's stored energy and can launch you? And then kinetic energy itself. If you are moving through space, that is the energy that is associated with that motion. So if we want to start to understand this on a deeper level, we do have to look at the mathematics. So I'm going to quickly go through. We're going to put a pause on elastic potential energy. We need to analyze springs, rubber bands, elastic properties in general before we can really understand that. So for right now, I'm going to present the equation for gravitational potential energy and kinetic energy. Then we can look at a few examples, and we will revisit elastic potential energy once we've had a chance to explore elastic properties a little bit more deeply. So to calculate gravitational potential energy, it's quite simple. Multiply your mass by your acceleration due to gravity, as well as your height. Mass has to be in kilograms. Acceleration of gravity, since it's an acceleration, needs to be in meters per second squared. And the height always needs to be in meters. If I multiply those three things together, I will be able to calculate Eg, which is my gravitational potential energy. Now, gravitational potential energy, any energy for that matter, is measured in joules, which is a unit you likely remember from chemistry. I do want to point out that because we are multiplying a mass, which is kilograms, times an acceleration, which is meters per second squared, times a height, which is meters, I get kg, I get two m's on the top, which is meters squared, and then second squared is on the bottom. So really, energy is measured in kilogram meter squared per second squared. That is the unit of energy. You will very rarely hear it referred to by that unit. We simply replace that with a joule. Just understand that a joule is that more complicated unit. It's just kind of a way to abbreviate everything and simplify some of our calculations. In terms of kinetic energy, it is also a fairly simple equation. I'm going to take 1/2 of my mass, and I'm going to multiply it by my velocity squared. Velocity is the only variable that's squared there. You're not squaring anything else. So take 1/2 my mass, square my velocity, and then multiply those two together. Mass must, as always, be in kilograms. Velocity must be in meters per second. And because this is energy, we're going to measure this in joules. Again, it's a kilogram meter squared per second squared, but we can simply say joules because it's a nice abbreviated way of representing that unit.